You wake up in the morning, you check your watch. It's 7:03 a.m. Time is flowing, as usual. You feel it's passing in every moment, every tick of the second hand. It feels universal, immutable, just there. But what if I told you that this flow of time is an illusion? Einstein's theory of relativity shattered the ancient notion that time is absolute. What you call a second is not the same for someone moving past you on a speeding train or someone floating above Earth in a satellite. Even your head is aging faster than your feet right now. Sounds crazy? It's not. It's physics. This chapter will take you on a journey through the strange, counterintuitive, yet very real effects of time, as described by Einstein. And most importantly, we'll show you how this warped time is affecting you every single day, whether you notice it or not.
Let's rewind a bit. Before Einstein, the world saw time as constant. Newton believed time was like an invisible, ticking metronome that beat the same for everyone in the universe. This was common sense. If your watch says 3 p.m. in London and someone else's clock in New York also says 3 p.m., surely those moments must be the same, right? Wrong. Einstein tore this idea down in 1905 with his theory of special relativity. His insight? The laws of physics are the same for all observers, but measurements of time and space depend on how fast you're moving. This isn't just a math trick. It's reality. He proposed something wild. Time is relative. Imagine you're on a spaceship moving at 90% the speed of light. To you, everything feels normal. But to an observer on Earth, your clock is ticking slower. This phenomenon is called time dilation. It's not theoretical, it's been measured and proven. GPS satellites must account for it daily. But more on that later.
Let's bring this concept down to Earth. Literally, you're standing on Earth's surface. Above you, at an altitude of 20,000 kilometers, a GPS satellite is orbiting the planet. That satellite's clock ticks faster than yours. Why? Because time flows faster in weaker gravitational fields, a result of general relativity. And because the satellite is moving at high speed, special relativity. These effects work in opposite directions, but they don't cancel out. Without correcting for time dilation, GPS devices would be off by about 10 kilometers per day. Every time you use your phone to navigate, you're relying on Einstein's corrections to time. That's relativity at work, in your pocket. But it doesn't stop there. Even the 30 centimeters between your head and your feet cause a measurable difference in how fast time moves. Your head experiences time a little bit faster than your toes. The effect is incredibly tiny, but it's real. You are, quite literally, aging faster at the top of your body than at the bottom.
Now let's explore one of the most famous thought experiments in relativity, the twin paradox. Imagine two identical twins. One stays on Earth, the other boards a spaceship, travels near the speed of light, then returns after a few years. When the traveling twin returns, he's younger than his sibling. This isn't a paradox, it's a prediction of relativity, and it's been proven. In 1971, scientists flew atomic clocks on airplanes around the world. When they compared them with clocks that stayed on the ground, the flying clocks were slower by precisely the amount Einstein predicted. The same thing happens to astronauts. When they return from space, they've aged less than people on Earth. Tiny fractions of a second, but measurable.
Time dilation isn't just a curiosity. It affects your biological rhythms, your technology, and your perception of reality. Let's start with biology. Your body relies on precise timing, heartbeat, circadian rhythms, hormonal cycles. All these systems are tightly synchronized. But what happens when time itself bends? Astronauts experience changes in heart rate, muscle tone, even gene expression during spaceflight. some of which may be influenced by the way time flows differently in orbit. Back on Earth, consider technology. Every financial transaction, stock trade, digital communication, or networked system relies on precise timestamps. These systems must correct for relativity, or they drift. If Wall Street ignored Einstein, billions could be lost in milliseconds.
Here's the biggest philosophical bombshell. The present moment doesn't exist everywhere at once. Let's say you're on Earth, and someone else is on a planet orbiting a star 10 light years away. If you're both stationary, you can agree on what now means. But if you move, even slightly, your idea of now shifts. Relativity says that simultaneity is relative. Two events that happen at the same time for you might happen at different times for someone else. This means the universe doesn't share a single present. It's smeared out across time. Your now is personal. This shakes the foundations of how we think about time. We tend to believe that the past is gone, the future hasn't happened, and we're moving through a universal now. But Einstein showed that time is woven into space-time itself, a four-dimensional fabric called space-time. You're not moving through time. You're already embedded in it.
You might ask, so what? These effects are tiny. Do they really matter? Yes, because they force us to confront the limits of human perception. We evolved to sense time in one way, linear, steady, reliable. But the universe doesn't work that way. Time is bendable, personal, even optional in a sense. We build our calendars, societies, and memories on a framework that isn't fundamentally real. It's an approximation, useful, but incomplete. Understanding relativity doesn't just let you build better GPS systems. It reshapes your sense of self, your place in the cosmos, your relationship to aging, memory, and destiny.
Time isn't what you think. It bends, it flows differently for everyone, and it affects every aspect of your daily life, from your phone, to your heartbeat, to the aging of your cells. And we're just scratching the surface. In the next chapter, we'll dive deeper into space-time itself, how gravity warps it, how light follows its curves, and how Einstein's equations might even explain black holes and time travel. So buckle up, because if you thought time was strange, wait until you meet the shape of space.